Okay, in this problem, which we've seen something similar to this before, we have the historical pass rate in a class of 70% or 0.7. So I'm going to put P as equal to 0.7. And in this case, now we have a sample size of 100. Now you can use the binomial formulas and the binomial tables to get this. It gets a little bit cumbersome, but it turns out that if you have a large enough sample size, that the distribution, the binomial distribution, starts to look like a bell curve. And in general, what we'll use for a rule, especially later in the class, is that if NP and NQ, now it used to be greater than 5, and then they said 10. I believe that the text that we're using right this semester says that both of those have to be greater than 15. Most texts, by the way, I think are still using around 10 right now, but whatever your book uses, if you're using something different than I'm using. But N times P is 100 times 0.7 is 70, and N times Q, remember Q is just 1 minus P. If 0.7 is the probability of success, then 0.3 is this probability of failure, or not making it through the course in this case. And both of those are greater than 15. So that means that we can say that the binomial distribution actually follows a bell curve. And it does so with a mean equal to NP, which in this case is 100 times 0.7 is 70, and with a standard deviation equal to the square root of NPQ, or the square root of 100 times 0.7 times 0.3, or about 4.58. I'm just going to redraw this a little bit, hopefully neater. A mean of 70 and a standard deviation of 4.58. And then it says find the probability that 80 or more pass the course. Now here's a little bit of a change here. We can't just go over and put 80 on our graph because we're using what in essence is a continuous curve. You know, there are no blank spaces on here. So we're using a continuous curve to estimate binomial probabilities, and binomials are discrete. You can't have 80.2 students pass the course. So 80 actually, here's 80 on our curve, actually includes another half on either side. In other words, it goes from 79.5 to 80.5. So everything between 79.5 and 80.5 is actually 80. So when it says that 80 or more, that includes all of this. So we're going to be looking at 79.5. And so when we do our calculations, it's just going to be z is equal to x minus mu over sigma. And it's going to be 79.5 minus 70 over 4.58. And that's going to give us 2.07. And so if we look that up in a z table, in a z table we go down to 2.08, and you should be able to see 4812 right there. So that means that this is 4812. And so the area out here beyond the 79.5 is 0.5 minus 0.4812 or 0.0188. So just under a 2% chance that we'll have 80 or more people pass that class. If we were going to use our TI calculator to get that probability, we could go to second distribution. Need to turn this on first. And, second VARS, which is to give us the distributions, and go to normal CDF, hit enter, and our lower limit is 79.5. Our upper is infinity, but you can give it any large number. I'm just going to, you can do some other things, but that'll do it. And then our mean was 70. And our standard deviation was about 4.58. And about 0.0190, so really close to what we have there. Of course, a little bit of rounding error. Okay, now I'm pulling up my R program for getting the Z area above a particular R. And so I'm just going to put 70, 4.58, and then the lower bound will be 79.5 since we're including all of 80. And then there we go. Okay, that doesn't, let me see if okay, that didn't show up until I extended that out a little bit. So to get the area above there, I'm going to just adjust the width and so on of my graph. And then once I have that, I can just export that. And I've got a graph I can put into my into anything I'm turning in. Okay, for part B, we want to know the probability that 65 or fewer pass the test. So we have our same mean and standard deviation that we had before, and we want to go from 65 down, but we want to include all of 65. So if this is 65, we would have to go halfway on either side of that for the 65. It goes from 64.5 to 65.5. So all of that is assigned to 65. Remember, we're using a continuous distribution to estimate discrete probabilities. But we want to have 65 or fewer, so it'll be from the 65.5 down. If it said fewer than 65, then we would go from 64.5 down. So our Z, x minus mu over sigma, is equal to 65.5 minus 70 over 4.58. And that's equal to minus 0.98. And if you look on the Z table, you might want to pause and do that and make sure you can do it. At any rate, it's 0.3365. So this is 0.3365. And then the area below that, all of that, is 0.5 minus 0.3365, or about 0.1635, it looks like. Okay, I'm going to verify that with my calculator, and I'm going to do second distribution, normal CDF, and I've got from minus 99999, that's negative infinity. Put any really low number, and we're coming up to 65.5 with a mean of 70 and a standard deviation of 4.58. Again, on that lower, you can put any really negative high number. Make sure you put a negative there because we're starting at negative infinity, really. And 1.629, that's pretty close. Here, that's probably just a little bit of rounding in things I did. Okay, in R, I'm going to pull up my Z area below program, and I'm going to set the mean to 70. The standard deviation was 4.58, and then the upper bound is going to be 65.5, and then just shade everything in and click run, and then we have our curve here. And that was, it's got the area below printed, the shading, everything you need there. So just export, copy to clipboard, copy plot, and you're off. That'll be it for this video.